All right, welcome back, everybody. Today we're going to be talking about the basics of confidence intervals. We're going to start putting together stuff we've learned in several different over the course of the year, and starting to put it together and to really apply the statistics to make educated guesses about certain values. So, after this section, which will be the next 2 days, you should be able to interpret a confidence level, interpret a confidence interval in context, describe how a confidence interval gives a range of plausible values for a parameter, describe the inference conditions necessary to construct the confidence intervals, and explain practical issues that can affect the interpretation of a confidence interval. So I said we'd be putting together a couple different ideas. So our goal in this unit is going to be that we're going to get a statistic and we're going to say, okay, how good an estimate of the population parameter is this statistic? Now in chapter 4 we talked about experimental design, and we learned that if you randomly draw a sample from a population, then you can use that statistic to make inference about the entire population. Last chapter, we learned that, hey, if we randomly select a sample, it's going to follow a certain distribution. And so what we can do is we can put those two ideas together, and if we do take a single sample, which is what we do in real life, as opposed to last unit where we simulated taking thousands of samples, we can say, okay, approximately how accurate is that sample? And that's what we're going to get into. We're going to get into this idea of a interval in which we are confident that the population parameter lies. So that's what we're going to be doing. We're going to be creating what are known as confidence intervals. And the key here is that we're going to use the idea of a sampling distribution. Now the sampling distribution was what would happen if we did infinite samples. And so a confidence interval is basically saying, hey, if you follow the same procedure as us, you're going to get a similar result. And the result is going to be described here in a minute. Remember, let's go back real quick. If you need to write anything down while I'm talking, just pause and note away. So a confidence interval. So if someone asked us to estimate some population parameter, if we were going to try and estimate some mean value, we would estimate it with x bar. If we were going to estimate a population proportion, we'd use p hat. And this is what's known as a point estimate. Is we're saying, hey, bang, there's our estimate. You know, if we're estimating p hat, right? If we're using this, the answer is going to be between 0 and 1. And they'll say, okay, what is p? And we're going to say, well, I don't know, but our sample was here. That was p hat. That's our point estimator. So a point estimator is a statistic that provides an estimate of a population parameter. Ideally, our point estimator is our best guess at the value of the unknown parameter. You know, as we looked at earlier, we'd want to pick a point estimator that was a statistic that had low variability and low bias. But we know that even if we get the variability low, there's always going to be some variability. That's, we chose at random. And so we have to think about our thing of not just this is what our estimate is, but how off could our estimate be? If we did it again, how close would we get to that same result? We know it's going to be slightly different because of the variability. And so here's an example. We have a population with a mean of 20. I don't know what we're measuring. If we gave everybody in Prince William County a math diagnostic test, the average score is a 20 if we did a census of the population. But we only take small samples of 16, and every time, this should be 200, sorry, not 20, something got cut off there. 250, I don't know what's going on with this. 240. Oh, it's giving me sigma, sorry. I apologize, I botched that. Let's start this whole slide over. So let's say, this is just an example. I don't know what mu is, but I know that sigma is 20. I know the standard deviation is 20, so I wasn't paying attention. So I take 3 different samples. Each one gives me a slightly different result. So what do we think the true mean of the population is? Well, I don't know what the true mean of the population is, so I don't know what mu x bar is. But I do know sigma divided by square root n is 5, and so I know my populations are going to be somewhere in here. You know, if I kept doing this. So these are probably in here somewhere. So what we're going to do is if we did this infinite times, we'd get a normal distribution. If you look at this, the original population was normally distributed, so the sampling distribution will be approximately normal. So we know that 68, 95, 99.7, you know, 1 standard deviation within the mean, 2 standard deviations within the mean, 3 standard deviations within the mean. That means that 95% of all samples of sample size 16 will be within 10 points of the true mean, which means that if we do this procedure 95% of the time, we will capture the true mean of the population. 5% of the time we won't, but 95% of the time we do this procedure, we will capture the population mean. And we're going to talk more about capturing in class. But the basic idea of a confidence interval is we have our point estimate, and then we have our margin of error. And our margin of error is what we're going to learn how to calculate in class next time. But this is going to be, say, hey, I don't know exactly. Let's say our estimate was p hat. We had the margin of error, and we're saying, hey, I don't know what p is, but I'm fairly confident it's going to be that it's in here. And it's a little bit more complicated than that. We're going to talk about the complications of that in class, but this is going to be the key idea, is creating an interval that we are confident that captures the true parameter of the population. All right. So the question then becomes, why don't we do something where we always get the answer? Well, we know statistics now. We know that in a normal distribution, it has tails. And so, you know, we could make the weather report correct 100% of the time. But the interval becomes so big as to be useless. So most of the time, we're going to go with confidence levels of 90 or 95%. 95% is going to be the most common. When you hear on the news when they report margin of error in polls, they are using a 95% confidence level. And we're going to talk about in class next time what confidence level means and how to interpret that correctly. But based on our confidence level, we're going to create some margin of error, and we'll be adding and subtracting that to our estimate to create an interval of possible values that we think capture the true proportion or the true parameter in the population. We'll start off with proportions first, and then we'll do means in the second half of the unit. So that's the video. I will see everybody next time, and we will get right into it in class.